Okay, so now let's do the hard part of the Neron-Ogg-Shafarevich criteria of Saar and Tate. So the hard part of the theorem. Okay, so here we're going to say that there exists infinitely many m with m is coprime to p, such that the so that this torsion here is unramified. Okay, and so this is going to imply that A has good reduction. Okay, and let's maybe put a subscript K here, because this is like the generic fiber of the Neron model. Okay, and so okay, and so let's do the proof of this. All right, so now what we're going to do is we're going to recall that AM, right? So by the structure theorem for AM. So now I'm going to go. I'm just going to go, and so what we're going to this so actually we're here we're going to show that AK. So this is A bar. This is the special fiber of the Neron model. AK over R, or AK over OK, is proper. Okay, so we have the generic fiber is proper, we have the special fiber is proper, and then I think to show that the Neron model is actually an abelian scheme, we need connectedness, and so we will get to that in a moment. Okay, and so all right, so by the structure so what am I doing? So yeah, I'm proving this that the special fiber is proper. Okay, so this is the definition of A bar. It's the special fiber of the Neron model. Okay, I'm like pronouncing Neron like a different way every time I say it. Okay, so by the structure of this thing, okay, so we did some counting. So we wrote this thing as an extension. So we wrote the connected component as an extension of the connected component of the special fiber as an extension of an abelian variety by an algebraic group. And the algebraic group breaks up as a unipotent part and a torsion part. And that allows us to count the torsion points, right? We have that, so that AM. Okay, so this was equal to the number so this is like a bounded part, so this is in a fixed finite group. It's not quite a finite group, but it's like bounded by the index of the connected component in the connected component inside the subgroup. Okay, plus, okay, and then we had the other part, which was M times 2b, that's the dimension of the abelian variety, plus S, that's the dimension of the torus. Okay? And so this gives us a nice little formula that AM here, bar. Okay, so the name of the game here is that we're going to, okay, divided by M, M, plus 2b plus S. Okay, so what we're going to do is we're going to compare like two dimensions and get a contradiction. Right, so M is really large, so it's going to be bigger than this. This is going to be less than 1, so this is less than or equal to greater than or equal to 2b plus S. If we take that really, really large, then that's going to be essentially 0. So, oh, I guess this is greater than or equal to 2b plus S. Let's see. So this is less than or equal to 2b plus S plus 1. And it's less than or equal to, so it's like 2b plus S. Okay, so this is what we have. We have this lower bound here and the upper bound here. That that's what we have. Okay, so on the other hand, so this is one thing that we have. So on the other hand, so we're gonna count in another way, right? So we have that this thing here, the invariance of the inertia is a bar of m. Okay, so sorry, we have inertia this is true, and so this is the invariance of inertia. So this is so this is equal to this is isomorphic to a. So this is an isomorphism. This is a of m. Okay, because we're invariant of inertia, and so this tells us that the number of a bar of m. So we're going to get another formula for this. This is the number of a of m that's invariant under inertia, which is just the number of a of m by hypothesis. So this is this unramified hypothesis. And this is equal to m times 2g. Okay? So, and we can combine these together. So combining these, so we have the following formulas, right? So let's do this. So we have m times 2g. So we have that 2g, okay, m divided by m. So we have this one, and that is going to be less than 2b plus s plus 1. And it's going to be greater than or equal to 2b plus s. Okay, so this is what we have. So, all right, great. So on the other hand, so sorry, we're not going to do that part. So now we can compute this in a different way. So we're going to get another formula. So so we can get another formula, and this is just looking at the structure of right. So the dimension of the special fiber is the same as the dimension of the Abelian variety, but we have this extension here. Right, so we have sorry. So this is 0. So this is the connected component. The dimension of the connected component is the same thing as the dimension of the reduction, right? And so this thing has dimension g. This is a product, right? And so this is dimension u plus s, and then this is dimension b. So the other formula that we get is that g is equal to u plus s plus b. All right, and so now we have two formulas together. So we get two formulas. We have that 2g. So this is 2b plus s plus 1. This is 2b plus s. And then we have g is equal to u plus s plus b. Okay? And so now, so this is nice. So now we have a system of equations which is going to lead us to a contradiction. Right? So, so actually, yeah, I guess we get equality here, huh? 2g is... So let me just look back here. So do we really get this lower one? Yeah, so that's a fixed part. All right, yeah, we do. So I guess we just get equality here. So because we can really take the floor on this side. Oh. I'm just noticing this now. So, okay, so this is an integer, right? So you can take the floor here. So this is some small number, and that's an integer. So then this is going to be, because we take m bigger than the index, and then this is just going to be that number. So yeah, we just get equality, actually. So if we want, this is 2g plus s. Okay, so either way, so now we just, what we'll do is we'll just plug these in. So here we get 2 u plus s plus b, and I guess we can write equals 2b plus s like this. Okay, and this tells us that 2u plus 2s plus 2b, this is equal to 2b plus s. This cancels and tells us that 2u is equal to negative s, right? And so these are positive integers, right? So that tells us that this thing is going to be negative, so, but it's also positive, so the only way for this to be negative and positive is for u to be equal to 0 and s to be equal to 0. Okay? And again, we actually can use equality here. All right, so that's what we have. And so this proves that that A bar, this connected component, is equal to B, right, or isomorphic to B, and hence that this thing here is proper. Okay, so so it remains to show that that A bar is connected. And that A bar is connected, and that we can conclude that A is an abelian scheme. Okay, and so a little trick, so a little bit more, will give you the rest of that, and I guess I'll do this part next.